Good morning, everyone, and welcome to our Geoscience Australia public talk. Apologies for being a little late starting. We did have some technical issues in the room, so we've moved to a fully online talk today. My name's Marie Wilson. I'm the Chief of Place and Communities Division here at Geoscience Australia. And I'd like to acknowledge the country that we're meeting on today, which is the lands of the Ngunnawal and Ngambri people, and I acknowledge their elders past and present. We at Geoscience Australia value the lands, water and sky as we work to deepen a shared understanding of country and earth. And we respect First Nations peoples and their enduring connection, contribution and obligations to country. Reflecting on our shared history, we are committed to listen and learn. So today I'm very excited to welcome you to the second presentation in this year's Distinguished Geoscience Australia Lecture Series, which is a series of presentations in prestigious recognition of GA's staff members' major achievements and contributions to earth science. So very excited to introduce to you today to Ricky Weber, who's presenting on urban seismic risk in Java, Indonesia. Ricky joined Geoscience Australia in 2009 and has worked in the natural hazards area since 2012. Ricky has a Bachelor of Science Honours in Geology from ANU, a Master's of Disaster Preparedness and Reconstruction from the University of Newcastle, and has recently submitted her PhD thesis at the ANU. Ricky has worked on earthquake and tsunami hazard and impact in the past, predominantly in Indonesia and the Pacific. Now, Ricky is the team lead of the Impacts and Atmospheric Hazards team, focusing on tropical cyclone hazard and risk in Australia and in the Philippines. So today we have the Q&A function enabled online. So as Ricky goes through her presentation, please feel free to pop your questions in there and we'll have some time at the end to answer. Thanks everyone, and over to you, Ricky.
Thanks, Marie. Thanks for the introduction. As Marie said, I'm presenting my PhD research, which was on urban seismic risk in Java, Indonesia. So before I get into it, I'd just like to do a few acknowledgements. So this research was supported by the PhD scholarship and also by the Research Training Program scholarship from the ANU. My supervisors were Phil Cummins and Mark Edwards from Geoscience Australia and Vitor Silva from the Global Earthquake Model Foundation in Italy. It was also undertaken with many supporting colleagues from GA and from overseas who gave helpful advice and reviews and access to data. And I'd also like to specifically mention the Statistics Office in Indonesia and the access to the 2010 census and household survey data, and this was accessed through the ANU Dataverse. So my talk today will be structured as the following. I'll give some background information, summarize the 4 research components of my thesis, and give some concluding remarks. So first off is motivation. So Java is the most populated island in the world. It's very densely populated. We know intuitively that there must be high seismic risk in Java, but there is a widely held perception that damaging earthquakes do not happen in Java, and specifically that they don't happen in Jakarta. But we do know that this is not necessarily true and that we need a greater understanding of seismic risk. So the Sendai framework says that understanding disaster risk is critical to move towards mitigation and prevention. This is also highlighted in the Sustainable Development Goals, and it's also highlighted by Indonesia scholars themselves who have said that seismic risk assessment is more likely to be effective in influencing disaster risk reduction policy in Indonesia than simply focusing on the hazard. So what is seismic risk? The UNDRR defines risk in general as the potential for loss of life or damage to assets that can occur in a specific period of time determined probabilistically as a function of hazard, exposure, and vulnerability. So we use this heuristic here where we have hazard, in this case, the ground motion intensity of an earthquake, times the exposure, which is the assets that experience the ground motion, multiplied by the fragility or vulnerability, which describes how these buildings would perform subjected to different ground motion intensities. And we can combine all these things to end up with risk in an economic sense. So we can, for one example, losses over a period of time. So what do we know about hazard in Indonesia? If we look at the figure on the left, this is an example figure of the tectonic setting of Indonesia, and we can see the major plate boundaries in the region and the relative motion. So we can see it is quite an active tectonic setting and the convergence of multiple plate boundaries. The figure on the right here is the earthquake sources that were used in the 2017 Indonesia probabilistic seismic hazard assessment. So you can see that as well as the subduction zones, there are many crustal sources that are contributing to earthquake hazard in Indonesia. This is the 2017 probabilistic seismic hazard assessment for Indonesia. This is a PGA map with a 2% probability of exceedance in 50 years. And so we've highlighted Java here in the red box. So you can see that Java has a high hazard compared to somewhere like Australia, but it is not the most hazardous region in Indonesia, though some scholars have suggested that the hazard estimates in Java itself are quite conservative, particularly near the major cities of Jakarta, Bandung, Semarang, and Surabaya. So the next thing we need to know about is exposure. So this is in terms of population and buildings. So the population of Java dwarfs the rest of the country with 151 million people, which is over 50% of the population of Indonesia living on the island of Java. In Jakarta itself, the population density can reach up to 16,000 people per kilometre squared. So with this many people in a small amount of space, we end up with a large amount of buildings. And we know that the buildings can differ significantly in Java, even within the one city. So all these figures on the right are from the city of Bandung. And so we have locations like the top left, which are a more common cityscape that people might be used to seeing. On the right, we have an example of a mass social housing development, and down the bottom, we have an example of a slum region in Bandung. So we can see that the buildings are differing in terms of quality of construction and style of construction, even within a small area. We also need to know about the vulnerability of the buildings, and we can infer this from past damaging earthquakes, that there is a history of damaging earthquakes and buildings are vulnerable and incurring damage from these events. So we look at the map on the top right. This is damaging earthquakes from 1980 to 2023. So all of these earthquakes are the red dots inflicted some kind of damage to the built environment in Java, and the locations that are highlighted in grey experienced some kind of damage to assets within this time period, and only the areas in white did not have any damage in that sort of 45-year time period. We do know historically more about damage. This is the work of Stacey Martin, and this dates back to prior to the 1600s. And we have examples of records of earthquakes that occurred and a relative intensity for them that's been estimated. So ones that are yellow to red are ones that we would expect to have caused damage in Java. And we know that one of these is for Batavia, which is modern day Jakarta. So we do have evidence, despite perceptions, of damaging earthquakes occurring in Jakarta. We also have evidence of these types of earthquakes in Java more generally, from the 2006 Yogyakarta earthquake, which caused extensive damage, the more recent 2022 Cianjur earthquake, and also an example of an 1879 earthquake in Cianjur. So it's not just that these places experience damaging earthquakes, but they're happening in the same location more than once. So we know that Java has high hazard, high exposure, and that the buildings are vulnerable to earthquake ground motion. So these are the elements required for risk assessment, but our understanding of risk is not very advanced in Indonesia or in Java. The most advanced understanding is part of the global seismic risk assessment that was undertaken by GEM. And so we've highlighted Java in the little box here. And so we can see that it has a high risk, sort of similar to other subduction zone regions in the world, but it doesn't tell us enough information about the variation across the country to support subnational or sub-island decision making. On the other side, we have a small scale assessment of risk in one area of Jakarta, and this only covers residential buildings. And so again, whilst it is fit for the purpose of the study, it doesn't give us enough information to have that spatial variation of risk and to support decision making. And so the purpose of this study was to improve our understanding of seismic risk and the associated uncertainty at the village scale in Java, Indonesia. And this was chosen as it is something that can be used to inform DRR policy and mitigation. So the way the study is structured is in 4 components: the Java exposure model, the fragility of houses, validation of the exposure model, and then moving on to incorporating all of the previous studies into a probabilistic risk model. Before I present my findings, some useful information that I will refer to throughout is that Java is divided into multiple different administrative levels, and some of the ones I'll talk about are province scale, which is shown in this figure here. So with the boundaries here, so there's 6 provinces. The map down the bottom is an example of Kabupaten, which is administrative 2 level, and and the coloration on this one is actually the village or decascale. So there's over 15,000 of these within Java. All of the modelling has been undertaken using OpenQuake, which is produced by the Global Earthquake Model. And the basic process is that a source model, a VS30 model, and ground motion models are required to produce a hazard model. And then from the hazard model, we get ground motion fields, and we combine this with an exposure model and fragility or vulnerability models to get an impact or a risk assessment. So introduction to exposure modeling. I wanted to develop a more rigorous and nuanced model for exposure in Java by integrating many multidisciplinary data sets. An exposure model requires information on the number and type of buildings, the location of these buildings, the construction costs of these buildings, and the occupancy. So the current knowledge of exposure in Indonesia is what is in the global model, but it lacks detail on building types and uses and appears to underestimate the number of buildings in Java. And then we have the small scale model, which supports the small scale risk assessment in Jakarta, which is only for residential buildings. So my model has 4 components: residential, commercial and industrial, schools, and hospitals. Underneath all of these headings, I have all of the multidisciplinary data sets that were integrated to produce each of these models. So you can see that the most information is available for residential buildings, and this residential buildings constitute over 70% of the building stock in Java. So what method was used for this? So small scale studies often use field surveys where you might survey every building or do a statistical survey of buildings in the field. This is not a small scale study. This is a large scale study, both spatially and in terms of the portfolio size, and these generally rely on census data as the primary input. So the method that I've used has been adapted from a method that was used in South America and is widely used for most exposure models that are produced at the moment. And so we have census data, and in the case of Indonesia, there isn't enough information in the census data. So we augment that with multidisciplinary data sets. We then need to, in parallel, identify and classify the buildings that are present in the environment and combine these 2 data sets with a mapping scheme. We produce an alternate mapping scheme to account for uncertainty. We harmonize with other data sets, calculate construction costs, and end up with an exposure model. So this is what the augmented census data inputs look like. We have all of the parameters on the left that are needed, and then the data sources and the references for these. I won't go through all of them. I'll just draw your attention to age. This is something that is commonly in the census of other countries that isn't in Indonesia. Age is really important as construction styles change over time. And so this was estimated using multiple eras of census data dating back to 1980. So this isn't something that is commonly done. And then we identify the buildings present in the environment. And so this is just an example for houses, not for any other building types. And so we have the general house type, an example of what they look like. We have an assessment of how many stories that they're commonly built to and what time frames that they're built to. For example, this specific unreinforced masonry building can be 1 to 4 stories high, and it has been constructed from Dutch colonial times until about the 1990s. So then what we do is we classify these with a taxonomy and a ductility, which explains how it will perform when subject to ground motion, whether it will be brittle or flexible. And then we can map that to our augmented census data. So this is an example of a mapping scheme. This is just for masonry houses. And so we're looking at the information from the census. We have that it's masonry. We have the setting from the census, whether it's rural, urban, or a city. We have our age estimate from the augmented data, our floor heights from the augmented data, and population below the poverty line from our augmented data, and we combine all of these to end up with a taxonomy which links to the building classification of the buildings present in the environment. Of course, there is a lot of uncertainty and subjectivity in this process. In Java, this mainly comes from the classification of masonry buildings. Masonry buildings have many different levels of performance, and so it's important to understand what the uncertainty is in that. So this is an example of a construction styles timeline for city regions. So we have pre-1990 unreinforced masonry, 1990 onwards confined masonry, and 2000 onwards reinforced concrete frame with infill walls. So all you need to understand is that these all perform differently when subjected to ground motion. So we have a simplistic model, which is what I just outlined to you, where we assume that the date on the timeline is where one construction style stops and another one is introduced. And then we have a phased model, which is more nuanced, where we assume that the construction style persists and there's overlap between the two construction styles as we go through time, and that this is dependent on the location and the poverty or wealth of a region. And so we end up with two models. And so just to highlight that in the simplistic model, we have about 32% unreinforced masonry at that island scale, and then it decreases to just under 20% with a phased model. So it does make a big difference to the buildings that are in the environment, and it is important to understand that. And these maps on the right here show what the differences are. So this is the difference when we're using the M2 phased model rather than the M1 simplistic model. So red areas are a reduction in unreinforced masonry buildings, and green areas are an increase in unreinforced masonry buildings. So it is nuanced, and it is important to understand these patterns across the island and when we move to risk assessment. So what does the exposure model look like? So this is the residential buildings. So we have the number of buildings per village shown here, and we have the exposed structural value per village here. And then we can see in the insets at the bottom, we have the Greater Jakarta region and the region surrounding Surabaya, which is the next largest city. And so in both of these, we can see that Jakarta is completely dwarfing the exposure in terms of the number of buildings and the value of these buildings. So how does this compare to other models? So we have the model of Lambang Go for West Jakarta, which I've mentioned. We have this study, and we have the GEM 2023 global model. So they're been undertaken at different resolutions. So the West Jakarta one is a building scale, mine is a village scale, and the GEM 2023 one is a Kabupaten, which is administrative 2 scale. And so then what does this look like in terms of the actual contents of the model is that we can see in the green highlighted that my model is quite similar to the building scale model. It's giving quite good estimates of the number of buildings, and that the GEM 2023 model is significantly underestimating the number of buildings within Jakarta by like 900,000 buildings. Another thing that is of interest is the number of building classifications or taxonomies. So in West Jakarta, there's 23 residential ones, which is the same as in my model. And then the GEM model, we can't extract at this, so we compare for all of Jakarta. Mine has 77 residential taxonomies, as opposed to only 9 in the GEM 2023 model. So what we can see here is that we're getting a lot of granularity of information, and we're getting quite close to what you can do with a building scale approach by using multidisciplinary data sets, which has advantages over the global approach. Okay, so in summary, for the exposure model, we've produced a village resolution model. There are 5 building uses included. There's 2 mapping schemes to account for the uncertainty in masonry house classification. There's improved accuracy due to use of multidisciplinary data sets. And also we've produced a qualitative assessment of confidence in the model parameters, which I show here. So for each building use and the parameters in the model, there's an assessment of the confidence in each of the parameters, so we can know how well we can rely on the model and also point to areas for improvement in future research. Okay, so the next component is fragility. So we're focused on houses, as most damage data collected in Indonesia is only for houses. So it's really the only part that we can study in detail. So fragility is a description of how a building will perform when subjected to different intensities of ground motion, and it has multiple damage states, so complete, extensive, moderate, and slight, as shown in the graphs. So all of these graphs are for the same building type from different studies. So they're all for a low-rise unreinforced masonry building. And you can see that they might use different intensity measures, and they also have different results. So for example, this one here with a 0.5 G is looking at a 50% probability of exceedance of complete damage. But when we look at this one up here that was developed for South America at 0.5 G, we're really only at about 10% probability exceedance of complete damage. So there's large variation in these functions. Our current knowledge is that there are some functions from a Padang damage survey that was undertaken. There are no validation studies. There's no other Indonesia-specific functions. So there's global data sets, there's hazard models which are used globally, and then there's analogues from other countries which we can look at. So the method for this is to select events that have enough damage data to be able to focus on the fragility functions and which best describe houses in Indonesia. So we've selected the 2006 Yogyakarta event and 2009 Padang event, as they were the only two events that had enough damage data at a fine enough resolution with enough information about the event itself as well to allow the detailed modelling. So in the selection of these two events, we needed to develop pre-event residential exposure models, so ones that represented the building stock as it would have been just before the event occurred, following a similar process to what I just described before, but ending in 2006 or 2009. Then scenario damage simulations were undertaken, and the results were compared to damage recorded on the ground, and also a sensitivity analysis was undertaken for ground motion models, VS30 models, as well as the fragility functions. And then we end up with some recommendations of how to move forward. So first off, VS30. VS30 is the shear wave velocity in the top 30 meters of the soil. It's important for the performance of buildings. It's important to include this. So there's the USGS model, which is commonly used, which is based on topography derived from SRTM data. And then in Indonesia, there is an Indonesia-wide model produced by Chipta in 2017, which is based on geomorphology as well as slope using methods developed in Japan. So we have comparisons of these for Padang and for Yogyakarta, and what we can see in both of them is that the purple areas are softer soil and the greener areas are harder rock, and that the Chipta model gives softer soils in both locations consistently. So this is more likely that there would be more adverse effects from ground motion on buildings if they're on these softer soils. So the results of the fragility, this is just a high level summary. So we looked at the ground motion models that give the best estimates of ground motion for the event. We first tested the ground motion models that are in the 2017 PSHA and found that they did not perform well. So we moved to testing ground motion models that have been found to perform well in other analogous settings like Japan, New Zealand, and Papua New Guinea. And so we did find that they overall give a better result when we're trying to simulate the damage that was recorded. Also, we found that the damage results are most sensitive to fragility function selection, and that the Chipta VS30 model gives the best results overall. In particular, in Padang, we found that it was really difficult to replicate the recorded damage beyond the active volcanic chain in Padang, so it traverses all of Sumatra. So we could perform well near the coast, near the trench, but on the opposite side of the volcanic chain, it was really difficult to replicate the damage data. There was basically no recorded damage on this side, but most ground motion models were still predicting lots of damage, and it led us to hypothesize that the active volcanism may be an important aspect that we needed to include in our modelling. A ground motion modeler was identified where it was possible to account for active volcanism and the effect that has on seismic waves, and we found significant improvements in the modelling. So then we need to see whether this is necessary to do in Java as well. So we used the findings of fragility of houses and our hypotheses about volcanoes to try and validate the 2020 exposure model. So to validate the exposure model, we need to select events that are within 3 years of 2020 so that exposure is more likely to be a good representation of the buildings that were present at the time of the event. And we wanted to select a range of event styles, and the events needed to have sufficient damage data to allow comparisons and preferably have a station recording. So these requirements really limited the amount of events that were available for selection. So there was only 5 as shown in the table and the map, and so we modelled all 5. So if you look at the map, the areas in grey experience damage in 1 or more of these events, and so we're really only able to validate in these locations and then hope that if it performs well here, that this is representative of the broader island as the exposure model was constructed in the same way across the island. And then volcanoes. So based on our findings in Padang, we need to examine the impact of volcanism and whether this is important for Java as well. So for active shallow crust events, we selected ground motion models that are from Japan and New Zealand. They've also been used in Papua New Guinea, where we also have the active volcanism. For interface events, we selected a ground motion model from Japan and also a model that has the ability to account for active volcanism. And for interest lab, we have two ground motion models that are able to account for active volcanic zones. So one is the JAL model, where we define these orange volcanic zones. This is based on seismic tomography. And then the Abrahamson et al. One, which defines back arc zones. So it's a different definition. It's just a line along the volcanic front. So these two functions or ground motion models operate in different ways. The Abrahamson one is quite simplistic to implement, and the JAL one is not, and it's also very compute intensive. So whilst we can use it for scenarios, we can't scale it to probabilistic hazard. So I'll just present a couple of the results because we don't have enough time. So one of the examples is from Chianjur, which is an active shallow crust event that occurred in 2022. So we tested all of the ground motion models that I just illustrated, and we found this Bradley one from New Zealand performed the best, but it still wasn't quite good enough. So this is the image on the right. And so we performed site conditioning based on a lot of station data to produce a ground motion field, which we feel is quite a good representation of the ground motion that actually occurred during the event. Then we test multiple things. We have the recorded data and we test the different mapping schemes of the exposure model, and we also test some fragility functions as well. And I won't go into the fragility functions because we don't have time, but what we can see here is that the mapping scheme 1 gives a really good representation of the recorded damage and is quite a good estimate. What I should also mention here is that slight damage is overestimated in nearly every simulation. This is quite a common occurrence, and this is because damage data is not collected for scientific reasons. It's collected for humanitarian reasons. And so the damage collection is focused on where the event had the greatest impact, and so you expect to be much better recorded data for heavy and moderate damage, and slight damage might be occurring further afield where there is less destruction from the event, and this is poorly collected. Another example is from Levac, which is an example of an interface event, and so we have maps on the left here that are showing the different ground motion models that were tested for this event. At the top, we have Abrahamson with no back arc region and with one implemented, and we have the JAL one, which doesn't have volcanic zones implemented for an interface style event. And so what we have is that this is really a small scale event. It didn't actually cause much damage. It's very difficult to try and simulate an event where there is sparse damage. However, we do have up here, if we look at the station residuals, we do have a good representation of the ground motion quite close to the event at this station in Sukabumi, and then it's sort of the quality of it decays as you get further away from the event, from the epicenter of the event. However, there isn't actually any sort of damage in that decayed region, so we're not as concerned about that. And this is what the damage data looks like. This is presented as a table because it's very, very small amounts of damage. But the things to highlight from this is that, for example, in Qianzhou, there was 0 heavy damage and 0 moderate damage, and we are predicting that. So this is important to as well, that we're not predicting damage where it doesn't exist. In some locations, we have quite good estimates, like in Bogor, of the heavy damage. It is a bit variable in some other locations, and this might be due to not a good representation of the ground motion, or it could be because of issues with the collection of the recorded damage data, or it just could be that it's a very small event and difficult to replicate. But if we look at the no damage column, we are really giving a good representation of the total building stock that is impacted or not impacted, and so this is good enough for our purposes. And so the next event I want to walk you through is the Tasikmalaya 2009 event. So you'll note that this event wasn't one of the ones that was originally selected because it's too far away in time from the exposure model. However, all of the events that were close in time to the exposure model are not very large events, and they weren't a very good demonstration of the impact of volcanic zones, and it didn't allow us to analyse whether it was important or not. So we decided to model this larger event, which does have damage data, with the understanding that we would be overestimating the recorded damage because there are more houses in 2020 than there were in 2009. And so what we have in these maps up the top is ground motion fields with the JAL model. So this is with a volcanic zone implemented, and on the right without the volcanic zone implemented. And what we can see in these maps is that when the volcanic zone is implemented, the strength of the seismic waves sort of deteriorates, and once you get to the north of the island, they are no longer at a damaging level. Whereas when there is no volcanic zone, you still have damaging earth ground motions propagating all the way to the north of the island. So it does make a significant difference in the ground motion fields, and the same thing can be seen with Abrahamson with the back arc zone. And so then when we compare to the recorded data, what we can see is we get the overestimation as we thought would occur because there's more buildings in 2020 than 2009. But the ones that give the best estimate of the recorded damage are all with the, so we tested 8 different simulations here, all the ones that have a volcanic zone or a back arc zone implemented to account for the impact of active volcanism on seismic waves. So this is reinforcing that this is important in Java as well. So the key findings from the exposure validation is that the results indicate that the simulation of recent damaging earthquakes using the Java 2020 exposure give a good approximation of the damage recorded post-event. There's spatial variation in the mapping scheme that gives the best agreement with the recorded damage data, and the results confirm the importance of accounting for regions of active volcanism. And so the Zhao et al. Ground motion model performed quite well, but it can only be used for scenarios. It's not able to be scaled to probabilistic seismic hazard assessment as it's too compute intensive. There is a continued overestimation of the slight damage category, but this is lesser when active volcanism is accounted for. So now we move to the final component, which is bringing everything together in a risk analysis for Java. So the way this is set up is that for the hazard, we have 3 different hazard model options to look at. For exposure, the 2 mapping schemes, which I've talked through, we use the global vulnerability functions, which are analogous to the fragility functions, but give you the economic losses. And then we look at the risk in terms of economic losses, fatalities, and uninhabitable houses, the sensitivity to the different input models. And we also look at a hypothetically less vulnerable exposure model. So for the seismic hazard inputs, I draw your attention to, this slide's a bit messy, but the table in the bottom right, we have 3 different simulations that we're looking at with a different combination of source models and ground motion models. So we have source 1, which is the original source used in the 2017 PSHA for Indonesia. And we have 2 ground motion logic trees, one that is a revised version of the 2017 PSHA, and one that was developed in this study based on the findings of the previous work I've just described. We also have an alternate source model, which has been adapted from a recent study and includes more crustal faults than are in the 2017 PSHA. So the table on the top left shows you the ground motion model logic trees that are used and the weightings on them if you are interested. We use the CHIPTA VS30 model for all of Java, as we found it performed well in all our previous scenario work. The map on the top right here is a zoom in of the map I showed you earlier of the crustal faults that are incorporated in the 2017 PSHA. And then this map here in the middle has the new faults that are included in source model 2 in this study. So this is particularly important for the West Java backup thrust, which runs through Bogor to the south of Jakarta, and the multiple segments of the Kendeng thrust, which has implications for the cities of Semarang and Surabaya that sort of lie along this. Okay, so we combine all of those hazard inputs that I just described to create an event-based probabilistic seismic hazard assessment for the whole island, and we produce some hazard curves as well. So on the left, we have hazard curves for the key cities, and we have how the hazard differs depending on which simulation was undertaken. So these are probability of exceedance of different levels of ground motion. So when you've got high probability and low ground motion, that's a more likely, a more frequent event, and you sort of have less likely and sort of more spaced out events typically as you move to higher ground motions and lower probabilities of exceedance. And so we can see in somewhere like central Jakarta that it doesn't make a significant difference in the hazard, but in all other key cities, it is making quite a difference, and we are significantly increasing the hazard if we're using the ground motion logic tree developed in this study and the source model developed in this study. And we should mention that that is our preferred model as it is based on the most recent science, but it is acknowledged that this is a high-end member of hazard. The maps here just show the similar data at the island scale. So this is PGA maps, 2% probability of exceedance in 50 years for the 3 different simulations. So simulation 1 is most similar to what was in the 2017 PSHA. In simulation 2, we're introducing a new ground motion logic tree, which accounts for volcanic zones. And so you can see that there is a sort of decrease in the ground motion predicted in the north of the island with the introduction of that ground motion model. And then in the bottom one for simulation 3, we've introduced the new source model with more crustal faults, and we can clearly see that is having an impact on the hazard, and those crustal faults are delineated there. So we combine the results of the hazard with the exposure model that we've already developed and the vulnerability functions to calculate risk. So we can look at risk in a few ways. So this is economic losses. So we have curves for key cities on the left here, and Jakarta is broken into its component parts. And we have 6 simulations now because we're looking at 2 different mapping schemes. So mapping scheme 1 for exposure is the solid line, and mapping scheme 2 for exposure is the dashed line. And so we can see in some locations the risk is quite similar. Doesn't matter what simulation you use. For example, in West Jakarta, but in other locations, for example, in North Jakarta, we have that the simulation that's closest to the 2017 PSHA in terms of hazard actually has higher risk, and the risk is decreasing with the other simulations. And this is because of the introduction of the active volcanic zones, and it providing a bit of a shielding effect for the damaging ground motions in the north of Jakarta. Other places we can see that the introduction example, Kota Semarang and Kota Surabaya, that the introduction of the new sources is having a serious impact on the risk in those locations, and it is just significantly different to when those faults weren't accounted for. And this is obviously because these now active faults that are running through or near these cities that are causing damaging ground motions. The figures in the middle show the similar data. It's for the 1,000-year return period economic losses at the coupled pattern scale for each of the simulations. So it just shows you how the losses are changing depending on which simulation is used. What we can see in all of them is that this coupled pattern to the south of Jakarta is Bogor. It has the highest risk in terms of economic losses in each of the simulations. And then we have this table here, which is a ranking table of the 10 coupled pattern with the highest economic losses for the 1,000-year return period for each of the 6 simulations. So what is noticeable in this is that Bogor is the one with the highest economic losses in nearly every simulation. But as we work through the rankings, it does change, and some coupled pattern are highlighted in one simulation and not in another. Information like this is really useful for disaster policy to prioritise areas for further studies or mitigation. And so this is just highlighting that you really do need to understand the uncertainty in your risk, because it might be a priority in one simulation and not in another simulation. So another thing we looked at was fatalities and uninhabitable houses. So this curve here is for fatalities over 1,000 years, and this is aggregated at the province scale. And so again, we have solid lines are mapping scheme 1 exposure, and dashed lines are mapping scheme 2 exposure. So we can see in places, for example, Central Java in the orange line, that it makes minimal difference which mapping scheme that you use. However, in locations, for example, like East Java in the green and Banten in the turquoise colour, that mapping scheme 2 is giving a reduction in fatalities. So this is an important consideration when we're looking at risk as well, not just to look at economic losses. The table down the bottom is for uninhabitable houses at the province scale, and it's the difference between the 2 mapping schemes that are used, and it shows you the percentage reduction in the number of uninhabitable houses when mapping scheme 2 is used. So you can see we're getting between a 16 to 45% reduction in the number of uninhabitable houses. So it really is important to understand what the exposure is and what the uncertainty is for this particular risk metric. If we moved over to the maps, at the top we have fatalities, and at the bottom we have uninhabitable houses. So in both of these, it is the mapping scheme 2 that is displayed, and then down the bottom we have the difference. So red and orange have higher fatalities or uninhabitable houses with mapping scheme 1, and black and grey have lower with mapping scheme 1. So you can see that it's spatially variable, and it is important to understand how this uncertainty plays out when you are considering these risk metrics. So sensitivity to input models for economic losses. So I sort of just ran through that for fatalities and uninhabitable houses. Those were only done with our favoured hazard model because they're quite compute intensive. But these ones were for economic losses were done with all of the simulations. So I've just shown some highlights of the results here. So we look at the sensitivity to mapping scheme, logic tree and source model, and we have up the top, this is mapping scheme 1, and the difference when mapping scheme 2 is used. Logic tree, this is logic tree 2. The difference when logic tree 1 is used. This is source model 2, and the difference when source model 1 is used. So in all of them, we have that grey and black is lower and red and orange is higher risk. And the things to look at here is that whilst the results are sensitive to all of these input model selections, they are particularly important for the source model in the areas where we've introduced the new crustal faults, where it can make it over 100% difference to the risk. And it is important nearly everywhere for ground motion logic tree, as it has up to sort of 50% difference in the risk depending on which logic tree is used. So after looking at that, we decided to just hypothetically think about what if a more resilient building portfolio was used. To create this, we just assumed that there was no longer any unreinforced masonry buildings and that all low ductility buildings became moderate ductility buildings, so they would perform better when subjected to earthquake ground motion. So we have the result here at the province scale. So we introduce another 2 simulations. And so basically we have that the purple is the original with the favoured hazard model and risk, and then the orange is with the new resilient exposure, and we can see in most locations other than Jakarta it makes a significant reduction in the economic losses. This table just shows the same thing, and we can look at but as average annualized loss ratio and gives the percentage differences. So in Jakarta, where we have more resilient buildings anyway, as it's a more wealthier location, we're getting between a 14 to 30% reduction in the risk. But in poorer regions where we don't have resilient buildings, like East Java, we're getting a 66% reduction in the risk when we have this more resilient exposure model. So the more resilient exposure model is not necessarily in line with the building code. It is just more resilient than the buildings that are currently in the environment. And information like this is useful for encouraging more resilient building practices and proving that it does indeed make a difference to your economic losses. So the key findings from risk analysis is that the economic losses are very sensitive to the ground motion logic tree and the source model selection, that fatalities and uninhabitable houses are quite sensitive to the exposure mapping scheme as well. The results highlight Kabupaten with the highest risk that could be used to prioritise more detailed analyses. Active volcanism is important to consider, particularly for Jakarta, and the inclusion of more active crustal sources suggests that the risk in Java is higher than previously thought, particularly in Semarang and Surabaya. So for future research, we're recommending for the exposure model that it could be expanded to include other islands in Indonesia and more building types, and that targeted field validation is conducted to make it more robust. We're recommending that there is localized fragility functions be developed. This relies on accurate capture of damage post events and also a good ground motion database. Linked to that is the development of localized ground motion models that better represent ground motion in Indonesia, and it would be recommended that they include the influence of active volcanism on seismic waves. It's also recommended that a retrofit cost-benefit analysis be undertaken to demonstrate the feasibility of retrofitting campaigns, and that factors other than economic losses like fatalities and displaced people should be considered. This research could also be expanded to include cascading hazards and risks. We know that earthquakes trigger tsunamis and landslides and liquefaction, and there's an example of all 3 of these occurring in the 2018 Palu event in Indonesia, and including all of these would give us a more holistic understanding of risk. So that's the end of my presentation. These are just the references that I have referred to. So thank you, and are there any questions?
Thank you so much, Ricky. That was really interesting. We do have a couple of questions in the chat. We don't have much time. I think for most of you, we'll try and get back to you at some point soon, but maybe just one question. So this is from David Robinson. Can you comment on how your findings, including the revised exposure information, is being considered by GEM in the update of the next global risk assessment?
Yes, thanks for the question, David. So I've agreed to share the exposure model with GEM. It's currently freely available on the GA GitHub. I have not had any recent conversations with them on how they are going to use it, because they did do a recent update to the exposure model before I completed this. So it wasn't included in that, though I did give them some advice. So maybe not in the next iteration of the global risk, but maybe the one after.
Awesome. Thank you so much, Ricky. I don't need you to answer now, but my question for later is how does Jakarta sinking affect its ground motion? Removing the groundwater. So thank you so much. Please, everyone online, please join me in thanking Ricky for what was a really interesting talk. And can I just say, for someone who is not a scientist in earthquake matters, I really appreciate it. I understood it all. So well done. Thank you very much.
Thanks, Marie.
So our next public talk will be on Wednesday, the 11th of June, when Karen Soldenhoff from ANSTO Jess Wash from Geoscience Australia and Mark Pearce from CSIRO. We will be presenting on advancing development of Australia's rare earth resources, integrated science to highlight the opportunity. So please do join us at our next presentation on Wednesday, the 11th of June. Details and the registration links for all of our public talks are available at ga.gov.au/news. And just click on the public talks title. So thank you once again, Ricky. That was fantastic. Thank you, everyone online. Thank you for asking your questions, and we'll respond to as many of those as we can. And please join us next time. Thank you.